Now we have everything we need to understand SAC, the Soft Actor-Critic, so by Harnoya and his colleagues, especially Sergey Levine from Berkeley University, and Peter Abil. There are two versions of ACC. They published the first paper, and then they realized that it was unnecessarily complex. And then there's this second paper where they simplified SAC, and I will focus on this variant. It's a bit easier to understand. I will skip some tricks, also just present the main idea. So what we have are these two equations linking the soft Q values to the soft V values. That's the Bellman equation. The value of an action is the expectation over the possible states of the immediate reward plus gamma, the value of the next state. And this new definition, the value of a state, is the expectation over all actions possible under the current policy, the Q value of that action minus the self-information of that action, or the negative log likelihood of that action. So we can do the same as in dynamic programming and write the Bellman equation. So you replace the value of the next state by its definition according to this formula, so in st plus 1, and you get this. The soft Q value of an action at time t is the expectation over the states you can arrive in, immediate reward plus gamma, expectation over the actions you can take in the next state, so at plus 1, Q value of the next action at time t plus 1 minus entropy of the policy in the next state. So we have an equation linking the Q value of an action to the Q value of all possible actions in all possible next states. So that's really the Bellman equation that we have already seen. And you see that the only difference is going to be this negative log likelihood in the next state. So now what are we going to do? We are going to transform this equation into an update rule, a loss function, that we will use to train a critic whose role will be to learn the soft Q values. So we have a neural network, Q5, whose role is to estimate these soft Q values, so to parameterize them with weights phi. And we are going to train that critic using samples. So here we have expectations over the possible states that you arrive in after the action. So we are going to sample one transition. We arrive in one particular state st plus 1, and we will just put that in a replay buffer to learn from it. Here we have an expectation over the action you will take in the next state, and again we will sample one action, compute this, and turn that into an update rule. That means your loss function for your critic is the expectation over transitions taken by your policy. So state st, action at, you arrive in st plus 1, so just observe this, it's a sampling operation. And you will compare the true value of your Q function, reward plus gamma, Q value of the next action minus log likelihood of the next action, to your current estimation, and you minimize the mean square error between the two. So that's really what we did for function approximation. That's the equivalent of Q learning or temporal difference learning, but this time using soft values. So how does it compare to what we have seen so far in hard RL, especially with SAC-Critic? We have mostly seen Q learning critics, but here that really looks like what SARSA would learn. Minimize the difference between immediate reward plus gamma, Q value of the next action, which will be selected by the current policy. And if you compare that directly to your estimated Q value, you have the SARSA-Critic. So that would be this term minus this term. That's SARSA. Q learning, that would be a max over the Q values. But we have now another term in the loss function of the critic, which is the negative log likelihood of this next action. So in the end, that's really the only difference that you have between hard and soft RL. It's just you want to estimate a Q value based on how much reward it brings, but also trying to make the policy as stochastic as possible. That's what the entropy means. In practice, the states, action, and next states can be sampled from a replay buffer. So that's what they show in the paper. If you sample them from another policy, you don't have a bias for the critic. It's only the next action at time t+1 that has to be sampled from the current policy by theta. But here you could use behavior policy B, and that would be exactly the same. It's only at+1 that has to be sampled from the current policy. But you don't have to take it. It means you can have an off-policy algorithm, still an actor-critic. So here we have learned the critic. We'll see how we can use this to train the actor. So it's an actor-critic, which is off-policy, so that can learn from a replay buffer, and that's going to speed up learning a lot. We have seen that off-policy methods have a lower sample complexity because they can reuse past transitions. But what we have seen so far was DDPG, which had a deterministic actor, which can overfit bad policies too soon. Here we are going to have a stochastic policy. So it's really the best of both worlds. It's off-policy, it's actor-critic, but the actor is stochastic. That's what makes SAC so powerful. What about the actor? So as said, our actor is going to be a softmax over the soft Q values. But now we have a critic that estimates those Q values. So our policy, pi theta, is going to be a softmax over the critic. We have seen that this normalization term, the partition function, is impossible to compute if you have continuous actions. We are going to note this z, so that the probability of selecting the action, the exponential of the estimated Q value of that action, soft Q value, divided by alpha, and then the term 1 on z that normalize it, so that it's a probability between 0 and 1 for all possible actions. The trick is that the actor has weights theta, but it depends directly on the weights phi of the critic. So actually we don't need weights theta, it's going to be the weights phi. So the trick they use in SAC is that the actor is still another neural network with weights theta, which will learn to be close from a softmax over the Q values, the soft Q values learned by the critic. These terms are probability distributions. In a state, you have different actions, or an infinity of actions if they are continuous. So this defines a probability distribution. And the only way we know to make two probability distributions close from each other is to minimize the Kullback-Leibler divergence between them. So the objective function, so the loss function of the actor, which will be to minimize the distance, statistical distance in the KL sense, between the learned policy, so what the neural network for the actor is learning, and the target, which is a softmax over the Q values of the critic. So that's two probability distributions, and when they are close from each other, which is what we want, then the KL is 0. Otherwise, it is positive. So it's something that we can really minimize. Now the cool trick is we can compute this. So we said z, we don't know it, and that's a big problem for continuous action spaces. In fact, by doing that, we will get rid of it. So the definition of the KL is I sample from one of the distribution, so from the actor, and I compute the minus the log of the ratio between the probability that the second distribution takes that action, and that's based on this distribution, divided by the probability that the first one you sample from takes it. That's the definition of the KL that we have already seen. Now we have the log between a lot of things. If we want to minimize this loss function, we are going to take the gradient of that loss function with respect to the weights of the actor and not the weights of the critic. So what depends on the actor here? So minus log, you see you have a product between things. So the log of a product is the sum of the logs. So you can expand this. And you see that you will have a log of z that will be in this expectation. But z doesn't depend on the weights theta of your actor. It's only depending on the critic. It's also not depending on the actions that you take with your actor, because that's over all possible actions. So when you take the gradient of this loss function, the part that depends on z will disappear. You have no participation of z in this gradient. So when you simplify, you see that you have minus log of pi that will stay here, and here you have log of exponential of q, so that will cancel. So the gradient of that KL is just the expectation over state and actions generated by the policy of alpha, the score, gradient of the log probability of your policy, minus the critic q phi for that action. So that's it. That's your policy gradient if you want, and it allows to get rid of this partition term. Well, that's really a very cool trick if you followed until now, because you can use an energy-based model, and everything is going to be linear and first order, so you can apply gradient descent. So in energy-based models like a restricted Boltzmann machine, you need to use complex sampling procedures like Markov chain, Monte Carlo Markov chain, MCMC, and the contrastive divergence algorithm. If you have a variational autoencoder, you need to do a variational inference. That's always very costly. But here it turns out to be a very simple update rule, and you can just apply this gradient, very easy to compute, to your actor, and TensorFlow will minimize it. And if you have an actor that implements a Gaussian policy, the grad log of the policy, you can compute it with the mean and variance, which are the output of the actor. So here everything is computable, and so you can really train SAC from end to end using a simple implementation. So here is the idea of SAC summarized. So SAC is an off-policy actor-critic architecture that implements maximum entropy RL. It means the objective function is not just maximizing the returns, but maximizing the sum of rewards while visiting states where the policy is as stochastic as possible. There is this parameter that controls the trade-off, the regularization. How much is this stochasticity important compared to the rewards? And in the paper, you can refer to details. It's even learnable. So it's not a hyperparameter. There's an update rule that allows to learn when to stop caring about this stochasticity. We have explored enough, so we can focus on exploitation. The critic learns to estimate soft Q values with an update rule which is like SARSA, which looks on policy but which can be off policy. And the only difference is that in the target for the Q values, there's the entropy term of the policy of that action. Actually, the self-information of that action. Surprising is that action. But that's the only change you have to train the critic. The actor is going to learn a Gaussian policy or a beta policy. There could be this variant also. And it learns to become close to a softmax over the Q values. So we solve the problem that Gaussian policies are unimodal, because here it's going to be close to a softmax over Q values. So it's going to be multimodal. If your Q values have different maxima, then the policy will take the maximum actions with high probabilities and avoid the others. So it's a way to use a softmax even in continuous action spaces. And the gradient is surprisingly simple, so you can train it with TensorFlow. So that's really the essence of SAC. In practice, that's much more complicated than that. So in practice, it uses clipped double learning, as in TD3. That means there are two critics, soft critics, and the target, which is used in the critic and the actor, is just the lesser of two evils. So the Q value that overestimates the less the true soft Q value. So I skip these details, really the same idea. There's no need for target networks because the next action 80+1 should be sampled by the current policy and not by the target network. It's also less memory hungry, so you don't need a copy of your neural networks and update them. So it's a bit faster to train. In TD3, if you remember, you added some noise also on the targets, so you didn't use the greedy action, so the deterministic action, but you added some noise in it in the target. Here you don't need it because your policy is stochastic, so this is sampled, so you don't need additional noise on it. And a set of other differences. So you can follow this link. So OpenAI has implementations of their algorithms, including SAC and TD3, so spinning up. And their documentation is quite good, especially they compare very well the differences between SAC and TD3. So that's the second version of SAC. That was the first paper they published, where they had another critic, another neural network that was learning the v-values. So here we are using the Bellman equation. If we come back to the beginning, we merge these two equations into one. You could also have a critic learning v-values, then using this critic to learn Q values, then use these Q values to train the actor. So the first version of SAC was learning both the policy, the Q values, and the V values. But the modern version of ACC has only policy and Q values. Here is a comparison on some continuous control problems. So the walkers, the cheetah, the ants, we have already seen these environments. And SAC has two versions. So the blue one is when you learn the temperature, so the parameter alpha. And the orange one is with a fixed value that you have to find as a hyperparameter. And it's compared to DDPG in purple, to TD3 in green, and to PPO in brown. So you see that PPO doesn't compare very well to TD3 or SAC. And then most of the time SAC is better than TD3, or at least equal. Here for humanoid, DDPG turned out to be better than TD3 for some reason. Doesn't converge at all, and PPO also not at all. You see, on this subset of experiments, SAC seems to be performing very well, and on all of them. If you look at the results, so here you have the Walker, the fact that you have the maximum entropy principle means that you are not learning a single strategy, a single policy, where you always run the same way. From runs to runs, it may really use different strategies, some more elegant than others, that make it very, very robust to changing environments. Here with the ant, so the spider, your goal is to find the blue square, and you have two passes to go there. You can go up or down, and during learning, this obstacle was not there during learning, so this is a legit path, but you can also go this way, and that's also an optimal function. If you don't have the maximum entropy problem, DDPG, for example, would converge on always doing the same action, which is going up. If you close the path, then it's going to be blocked, and it has to relearn everything from scratch to reach the goal from the bottom. SAC has been forced to explore both options, to go up and down. And if you block the goal, one of the paths, then it knows how to take the second, because it has explored it during learning. And paradoxically, in some sense, learning all solutions to a problem is faster than learning only one. So because you have so much exploration in SAC, you are understanding your world faster, and in the end you will need less samples than the other methods, which can end up being suboptimal in addition. So here is a video that shows that you can use SAC even in real time. So it has a low sample complexity and high robustness because of the stochastic policies. You can watch the full video if you want. So here they have a quite complex robotic problem. So we have a robot with 4 legs, which are very hard to control. And the reward is the speed in the forward direction. So the faster it goes, the more reward it gets. It's a quite complex control problem. And they use ACC to train it. And you see that very fast, after 18 minutes, it's going forward, it's not perfect. It still falls. And well, you can watch everything, so quite soon it's learning a correct policy. It's always going forward. It has learned to advance in less than 2 hours of real-time physical training. And the cool thing, so it can learn fast, and then because the policy was stochastic, it explored a lot of actions, not just the ones that were the best during learning, but really everything, because it's forced to do it. Then it can adapt to changes in the environment. So that's on the flat terrain it was trained on. And then when you test after learning, you can introduce difficulties. Of course, it's not what it was used to, but it explored so many variations that in fact it can cope with this additional things like steps. Of course, it must not be too hard. Obstacles. Still kind of the same policy, but it's really robust to these changes. They also applied SAC on a robot, so a robotic arm. And the goal is to stack Lego bricks, with the big Lego bricks, and just the goal is to have it on top of the red one. So it's a complex control problem because you have a lot of degrees of freedom in that arm. And in 2 hours, live on a single robot, it's able to learn a policy. So you could have distributed learning also in SAC because it's off policy, but here it's really a single robot. And the thing is that during learning, it explores any possible combination, and so it becomes robust to perturbations. After learning, you can really move the robotic arm and perturb it, and it's always recovering because it has seen everything it needs to recover from these perturbations, even if there was no perturbation during learning. That's really a very impressive property of SAC. And that's why maximum entropy algorithms, such as SAC, are now used a lot in robotics. Here are a couple of references if you want to go further. So Sergey Levine, so Berkeley, they work with Google. So here they describe the algorithm. Here two blog posts which explain how it works, also with some implementation. Here a blog post on soft Q-learning, so the predecessor of SAC, which is good also to understand the principle of maximum entropy. Here was a review by Sergey Levine on maximum entropy algorithms. It's a bit more advanced, but you can have a look at it.